So how do scientists figure out population sizes, and why is that important? Well, it's important to have a good understanding of how many of certain species we have out there, and scientists work pretty carefully at determining those numbers. This is to monitor populations that are at risk of becoming endangered. This is to gauge and measure the health of ecosystems by looking at critical or keystone species. And there's a whole range of other reasons to monitor the size of populations. One other reason I'd like you to consider now is thinking about this pandemic of COVID-19, that oftentimes epidemics and pandemics do follow exponential growth curves, at least for a little while. And so we're going to see that some of these calculations that we do in AP Bio are actually similar to ones that that doctors and scientists around the world are doing to try to figure out how fast diseases spread through populations. So it's a similar way of thinking, but we'll keep this focused on actual population sizes of different species for right now. So I'm going to go to the paper here. Actually, we're going to go to the formula sheet. I'll link to the formula sheet. I'll make sure this is linked under our reference tab, but you can always Google the AP Bio formula sheet. On the back of the formula sheet, we have our rate and growth calculations, right? So rate calculations we've been doing all year, and they kind of present it in a new way, dy over dt. That little lowercase d is from calculus. I don't want to scare anyone there, but it just tells you how much, it tells you the meaning of all these variables here. So this is just the amount of change over the amount of time. The D you can think of as change. So change in some variable over a change in time, which is really what we've been doing all year. Now, you can see some other information here about births and deaths. It's actually quite simple what biologists do to calculate growth rates. You need to know N, the population size. You need to know the number of births, which is big B. You need to know the number of deaths, which is big D. And that is about it. For whatever reason, you do not need to incorporate immigration and emigration, individuals entering and leaving the population, in these calculations. So the other variable I'd like to introduce right here is lowercase r, which is rate of growth. And the formula sheet lists this as R max, which would be our max per capita growth rate. I'm just gonna note this here as rate of growth. We'll talk about per capita, what that means in a little bit. So let's say an example here. Let's say we had a population of, I'm just making this number up, 1,100 individuals of some species, right? And let's say that we had in a given generation, or you could say unit of time, year maybe, we had, I don't know, I'm just making this up, 57 births and 23 deaths. So what I would do is I would calculate births minus deaths, and I would divide that by the total population size. So I'm going to go to my trusty calculator here and confirm that 57 minus 23 is 34. So here's 34. 34 divided by 1,100 is 0.03. So our R max for this population is 0.03, which is a rate of growth of 3%. So if I wanted to figure out how many individuals there will be in the population in the next generation, all I do is I take my population size and I multiply it by my R max, and then I add that number to the population. So if, you know, year one, and I'm just using year as an arbitrary unit of time. They might refer to this as generations or something else. If year one is 1,100, the amount of new individuals added, right, would be, I'm going to do 1,100 times 0.03. That would be that would be 33 individuals added to the population. This number then just gets added to this, so year 2 will be 1,133, right? Multiply this by 0.03 to get the number of new individuals added. I should make this a plus sign, sorry. And we can just keep going up from there. Now, this would lead to a growth curve that looks like this. And I'm going to make another video to show you why.